Alrighty, I hope we're doing okay, guys. First video was largely sort of explaining where the mean value theorem comes from, how it relates to stuff that we've done before, and then sort of doing one example. That's certainly not sufficient to solidify your understanding of the mean value theorem, hence, more than one video. Let's go ahead and jump right in with another example. And by the time we get to the end of this, I think you're going to understand the general tempo of all of this, and if not, of course, you're more than welcome to email me. Now, this is just a regular polynomial function. It's a cubic, and we should actually remember kind of what this looks like, because we should be able to take this and know that it factors into this. So we know that a cubic can have as many as 3 zeros, but we see the fact that we're only going to have 1 zero. It's actually going to go through the origin. And then, of course, we're going to have two imaginary zeros here, plus and minus root 2i. So it's nice to know kind of what it looks like ahead of time before we start getting going. But basically, you're interested in the interval -1 to 1. Well, here's the great thing. In order to satisfy hypotheses, there's nothing easier than a polynomial function, because you know that a polynomial function is continuous everywhere because it has an implied domain of -infinity to infinity. So f is continuous on -1 to 1. You know that it's everywhere differentiable, okay? I even used that word back in Algebra 2, though at that point you didn't know what it meant. I just told you that for all intents and purposes back then, especially relating to polynomial functions, it basically meant it was a smooth curve, okay? So anytime you have a polynomial, satisfying those hypotheses ought to really be no big deal, okay? So you know that it's continuous, you know that it's differentiable. The question is, where is the point in the interval where the instantaneous rate of change is equal to the average rate of change? Well, let's go ahead and actually find that average rate of change, okay? Rate of change. I don't know how else to abbreviate it, whatever. So we have f of 1 minus f of -1, right? F of b minus f of a over b minus a. And f of 1 is 3, and f of -1 is -3. And so that winds up being 6 over 2, or 3. Okay, well that's kind of nice. We know that the average rate of change of that particular function over that interval is 3. Okay. What I need to know now is what the derivative is. Okay, so this sort of block that out. We have f prime is equal to 3x squared plus 2. Now the question is, when is this equal to this? Okay, well, let's just go ahead and set them equal to each other. Okay. And we're going to get x squared after we subtract 2 and divide by 3 is equal to 1/3, but let's go ahead and call it 3/9 because I know that I'm going to be taking the square root here, and I know that x is equal to plus or minus root 3 over 3. Well, guess what? Both of those values occur on your interval, right? Because root 3 over 3, if root 3 is approximately 1.732, which is just a little bit less than 1.8, then divide that by 3, and it should be a little less than 0.6, okay? So root 3 divided by 3, and you have 0.577, okay? So that's plus or minus 0.577. And the great thing about actually doing it in terms of decimals here is just to confirm that it's in your interval, okay? But you actually should have recognized that. You should know the general magnitude of this number right here. So those are the two values on that interval that actually accord with that. Let's go ahead and actually look at. Let's go ahead and look at that function. So I have x cubed. Actually, let's go ahead and put that in x1. We have x cubed plus 2x, okay? Now, let's go ahead, and I know that if the slope is 3 and it goes through, and the output at 1 is 3, the output at negative 1 is negative 3, I happen to know that that's going to be y is equal to 3x. Okay? Let's go ahead and do it on the window negative 1 to 1. And of course, I know what my parameters are in terms of y outputs. And we can actually draw that. And here comes your cubic. Okay, and here comes the average rate of change. That is your secant line right there. Okay, now notice that right about here and right about here, you can actually have tangent lines that would be parallel to that secant line. So while the mean value theorem only guarantees in the abstract that there will be 1 on the interval if the hypotheses are satisfied, this one actually has 2. Okay, and you could, I mean, it's an irrational number, so it'd be kind of a pain in the rear end to actually find those tangent lines, but you could actually go and find those tangent lines and actually graph it and all sorts of fun stuff like that. I'm not gonna do that, but you could. I think it's going to be better off if we actually get along to another example. So let's go ahead and jump in with that. I want to walk through several of these with you so that, you know, by the end of it, you're like, okay, I generally understand what I need to be doing. Basically, anytime you're given one of these, let's say I'm given f of x is equal to x to the 2/3, and I'm interested in the interval from 0 to 1. The first thing that needs to be done is you need to satisfy the hypotheses, okay? You need to determine whether f is continuous, okay? Is f continuous on 0 to 1? Well, and that's supposed to be a 0. Okay, 0 to 1. Well, is there any place where this is going to be discontinuous? And the answer is no. I mean, you got to remember that when you're dealing with a fractional exponent, that's a cube root. And a cube root, you can take the cube root of any number, including negatives, right? Odd roots are fair game in terms of taking negative roots. And therefore, there's no reason why you can't plug any number that you want into here, okay? So the implied domain of the given function is negative infinity to infinity. This is continuous naturally on negative infinity to infinity. So it's certainly continuous on a subset of that, okay? Now f prime in this case is 2/3 x to the negative 1/3, which of course is 2 over 3 cube root of x. Now this is discontinuous at 0. But notice that when you're asking about whether it's differentiable, it is on the open interval. It doesn't include the endpoints. And this is kind of why, okay? Basically, you're evaluating whether f prime is continuous on the open interval, and if the only value for which f prime is discontinuous is 0. 0 is not included on the open interval, i.e. the non-inclusive interval, and therefore f is indeed differentiable on 0 to 1. So the first thing that you did is you determined whether it satisfied the two hypotheses. F is continuous on the closed interval, f is differentiable on the open interval. And in the meantime, you've actually already achieved the derivative of f. Now, since I know that those are the case, I know that there's going to be a point inside 0 to 1 where the instantaneous rate of change is equal to the average rate of change. Well, the instantaneous rate of change I can find when I set it equal to, but I need to find the average rate of change, right? So average rate of change, again, still haven't figured out how best to abbreviate that, but it doesn't really matter. I know that it's going to be f of 1 minus f of 0 over 1 minus 0, and that winds up being 1 over 1 or 1, right? Because you evaluate this at 1, and 1 to the 2/3 is 1. 0 to the 2/3 is 0, so 1 minus 0 over 1 minus 0 is 1 over 1 or 1. Okay, so now I need to figure out exactly where this derivative is equal to 1. Okay, so let's go ahead and find that. I know that 2 over 3 times the cube root of x is equal to 1, or the cube root of x is equal to 3/2, which means that I'm going to cube, I'm going to have to cube both of those, and I'm going to get x is equal to 27 over 8. Okay? Now, hold on. Oh, I messed that up somewhere. Where did I mess that up? Oh, yeah, because it's that. Okay, yeah, just sorry. And so it's the cube root of x is equal to 2/3. Sorry, I forgot that that was in the denominator. And therefore, x is equal to 8 over 27. Now, 8 over 27 is certainly well inside that 0 to 1 interval. Okay. Yeah, if the hypotheses are ever satisfied and you wind up getting something that doesn't make sense or is not in your interval, you have made a mistake, right? Because the mean value theorem dictates that it must exist. And if you found out that it didn't exist, then you've made a mistake somewhere. Thankfully, I caught that really quickly. So, alrighty, let's move on to another example. Let's look at... oh, this might actually be a good segue. Okay. Let's say f of x is equal to sine x, and I'm interested in 0 to pi. Okay. Well, I know what sine x looks like. Okay, sine x is definitely continuous on negative infinity to infinity, so it's definitely going to be continuous on a subset of that implied domain. And I know that its derivative cosine has the same domain, so f is definitely differentiable everywhere, and therefore it's definitely differentiable on this open interval from 0 to pi. So check, check, okay? I've satisfied both of them. And of course, like I said, the derivative of sine is cosine. What I need now is I need to find the average rate of change, okay? And that's going to be f of pi minus f of 0 over pi minus 0, or 0, right? Because sine of pi is 0, and sine of 0 is 0, so it's 0 over pi, or 0, okay? So this actually winds up telling me that the average rate of change of sine x from 0 to pi is 0. Well, that makes sense, because you should know that that's just one hump of the sine function, right? And then of course it kind of continues to go down here, and it winds up back here at 2 pi. So basically from here to here, it went up and then down, but your average rate of change is 0 because it went up just as far as it went down. That makes sense? And there's a certain symmetry to that hump between 0 and pi. My rough sketch didn't actually capture that very well. So the question is, when is the derivative equal to that 0 average rate of change? Well, we know that. We know that cosine is 0 at pi over 2. So we know that this has a horizontal tangent line up here, a slope of 0, right at the top, right at pi over 2. And you're familiar enough with the sine function and the graphs and the periods and everything like that, that this should make a whole lot of sense, okay? This is a nice segue into talking about Rolle's theorem. Rolle's theorem, and you really only need to know this insofar as your book is going to use the term, because Rolle's theorem is basically just a corollary of the mean value theorem. Whereas the mean value theorem states, 1, f is continuous on A to B. Number 2, f is differentiable on A to B. The Rolle's theorem has a third stipulation to ensure that the average rate of change is 0, and that's just f of A is equal to f of B. So that right there is just an added premise. And of course the conclusion is that there exists a value of C in AB, okay, such that, well, you don't have to put f of b minus f of a over b minus a. It's just f prime of c is equal to 0. Okay? So basically all you're doing is you're just adding a special third hypothesis, which basically just says, hey, by the way, this is mean value theorem. This tells me, this third hypothesis simply tells me that I'm dealing with a specific instance, a specific variety of mean value theorem question, and it happens to be when f of a is equal to f of b, making, of course, you know, if that's the case, then f of b minus f of a, the numerator of that secant line, right, is 0. If those two values are equal, then that difference is 0, and therefore the whole quotient is 0, right? So basically this is basically the conclusion. And of course that is exactly what we see here. We talked about it as a mean value theorem question, but as a specific instance of that, you know, being a specific case of the average rate of change being 0, leads us into, and this is Rolle's theorem. But nobody besides the writers of calculus books really care about that. We're going to go ahead and do maybe one more video on mean value theorem. While it isn't really all that complex, this is an incredibly important concept and section for the AP exam. There is always, and I'm pretty sure it's always, at least one part of there's at least one part of one of the free response questions that is a mean value theorem question. Oftentimes it's more than one across the 6 questions, and there will certainly be mean value theorem questions in the multiple choice. When AP calculus teachers get together and talk about how to prepare their students for AP calculus tests in May, when we have those little conferences where we all get together in San Antonio at a hotel and all talk about calculus all day long, the one thing that there is always a discussion of, where there's always a seminar on, is mean value theorem and how it is tested on the AP exam, because it is always there. Okay, so be sure that you're getting this material, even though it really isn't all that complex, because it will come back around in May. Okay, so be on the lookout for video number 3. As always, if there are questions, please do email me. See ya.